Hello. Today we are looking at how we can measure 3D objects with the SmartRunner Measurer 3D.
Objekte vermessen können.
The sensor outputs the volume, dimensions, rotation, and position of an object. These results are relevant for various applications. For example, as objects move along a conveyor belt, you need their dimensions so they can be sorted by size. Rotation is also important for when you need to determine both the dimensions and the orientation of objects before palletizing them. For this demonstration, we have already mounted our SmartRunner above a conveyor belt. The technology we use here is stereo vision technology. This is based on two 2D cameras integrated into the sensor, one on the left and one on the right, that capture 2D images of the scene from different positions. At the center of the sensor is a projector that casts a unique pattern onto the scene. This pattern supports the matching of the two 2D images, which then creates the depth image, the 3D information. To set up the sensor, we start our visualization and configuration tool, Visolution. In the device overview, we have the option to either search for sensors on the network via the refresh button, or to connect to a specific sensor with a known IP address via Add Device. We select the sensor that we have mounted here. Welcome. That's basically our start menu. Here we have various options. We can use the wizard for the raw data SmartRunner 3D. Since we are not using the raw data version here, we switch to expert mode. From this interface, we can also perform firmware updates via Maintain, as well as import or export configuration files via Transfer Configuration. Now let's click on Expert. Here we see the 3D point cloud of the conveyor belt. To better adjust the parameters, we can also place the first object on the conveyor belt. For this demonstration, we first place a cardboard box on the belt. At the top, we see the parameters that are relevant for image capture. For the trigger option, we can either trigger the sensor using a hardware trigger or run it in auto trigger mode, which is what we're doing here. What's clear here is that we get significantly fewer pixels coming back from the black surface of the conveyor belt. On the other hand, the cardboard box is very cooperative. It reflects a lot of light and gives us good data, so we see many more pixels. Since we want to measure the cardboard box, we can reduce the exposure time parameters here so that we have the optimal capture of the box and not the conveyor belt.
Damit wir die optimale Aufnahme des Objekts haben und nicht die optimale Aufnahme des Förderbands.
If we scroll down, we see the parameters that are relevant for the application for this sensor. This includes the reference plane, which means we need to set the distance between the sensor and the conveyor belt here. In this application, we can manually set the distance between the sensor and the conveyor belt. For this, we first switch the view to bottom and can also display the sensor and the grid for better orientation. If we zoom in, we can see that in the current setup, the origin of the coordinate system is at the front of the sensor. We want to shift it to the reference plane since we want the positions relative to that reference plane. In our setup, as you can see here, the distance between the sensor and the conveyor belt is 1.6 meters. We can adjust this value here. What's important is that we shift the coordinate system downward along the z-axis. We have a right-handed coordinate system. X and Y remain in their orientation, but since we're shifting it downward, we shift it to minus 1.6 meters relative to the camera. We've specified that here. Now, when we switch the coordinate system to the reference plane, you can see, illustrated here with the blue and red lines, that the reference plane is at the origin. Next, we can set the region of interest. This is especially relevant when we have an application where a sidewall of a conveyor belt extends into the image or other objects are visible that should not be considered in our calculation. We switch back to the front view to first set the region of interest in the X and Y axes. We can use Visualize ROI to display it, and we can now, for example, reduce the region of interest somewhat, and we can see how it adjusts.
Den Region of Interest etwas reduzieren und wir sehen, wie sich das Ganze anpasst.
Next, we can adjust the region of interest in the Z-axis. Since we have shifted the coordinate system's origin to the reference plane, the lower value is now 0, and in the direction of the camera, which points along the negative Z-axis, we enter the height of the region of interest.
Was ja in minus Z geht von der Richtung, geben wir praktisch die Höhe des ROIs ein.
And for our setup here, 20 centimeters is sufficient. After setting the region of interest, we can hide it again and look at the result, the object measurement. For this, we can visualize the result, and it's displayed using a bounding box. For a better view, we can hide the grid again. The results are displayed here in the lower left area. The first result is the rotation. The rotation refers to the x-axis of the longer side of the object. We can also output the volume, length, width, and height of the object. The first value in the dimensions is always the longer side. The fourth result is called center, or also position. It outputs the position of the object relative to the reference plane, and we output the coordinates there. One advantage of our sensor technology is that we have the ability to take static images. This means we get the information of the scene in X, Y, Z with one shot, and can therefore measure an object like a cardboard box or other objects, even while stationary. We can just as easily capture dynamic scenes. This means that if the object moves on the conveyor belt, or even if the sensor moves, it doesn't affect calculation of dimensions, volume, rotation, and position. Before we start the conveyor belt, it's important to remember that we have set a region of interest. This means we have limited the field of view of the sensor monitoring the conveyor belt. And if the box leaves the region of interest, as you can see here, only a small area of the package remains within the region of interest. Only that part is used for the calculation. The part of the box that is outside the region of interest is ignored. Due to the small setup, the belt in this demonstration is running at a reduced speed. However, the sensor can measure objects moving at speeds up to 2.5 meters per second. Next, let's take a look at how the application handles objects with irregular contours and shapes. Because the sensor can measure more than just box-shaped objects. To demonstrate this, we're placing a shipping envelope on the conveyor belt. As you can see, this shipping envelope has different heights, lengths, and widths. For irregular objects, a bounding box is placed around the contours of the object, in this case, the shipping envelope. The dimensions that are output refer to the measurements of the bounding box. The orientation of the object also refers to the bounding box. There's one special feature I will mention when it comes to volume calculation. We don't calculate the volume of the bounding box. Instead, we calculate the volume of the object. Shadowing can occur since the sensor only sees the surface from above. As a result, the calculated volume is an approximation of the object's actual volume. Next, we place a bundle that is typical for retail logistics on the belt. As you can see here, the individual cans and their contours are recognized, but it measures the entire bundle as one object. Which is very important for processes such as palletizing. Here, you can see that objects with all kinds of surfaces can be placed on the belt and measured. Even shiny metallic surfaces like these cans aren't a problem for the sensor. However, if we encounter more challenging surfaces such as black foam, we can easily adjust the parameters for image capture. Especially with dark objects, we have the option to make adjustments via exposure time and gain. If we increase these values, we see a significantly stronger signal, which improves the quality of the results. Compared to vision systems, we have the advantage that the evaluation of the image data takes place directly in the sensor. This means we don't need a separate evaluation unit or IPC. We get the results straight from the sensor and can use them directly in our applications. If you have questions or interest in our product, please feel free to contact Pepperl+Fuchs.